All right, let's share the screen and get going. All right, welcome to Chapter 11 of Geology for Gimmick Community College. Sorry, not Chapter 11, Chapter 1, my bad. Open up the participants and the chat window so you guys can talk to me if you want. I wouldn't mind it. And yeah, let's scroll through. So, as I've said previously, make sure to interact in the comment section or during this live presentation, whichever suits you best. Answer questions that are sent out to you, and let's get into an introduction to geology. First of all, what is geology, right? Geology is the science that pursues an understanding of our planet Earth. You could extrapolate that out to be not just the planet Earth, but for the sake of this class, planet Earth. We can talk about it in two senses: physical geology and historical geology. Physical geology is essentially geology of what we have now. And historical geology would be the geology of how it became. Historical geology would be the foundation of the continents, the magnetic field, things of that nature. Where physical geography would be how rivers form, what's happening with the mountain chains, where to find oil, natural gas, and other natural resources. You can think of geology not just as rocks, also people and the environment. Many important relationships between people and the natural environment include natural hazards, resources, population growth, and environmental issues. Geology plays a key factor, a key role in all of these. The nature of Earth has been a focus of study for upwards of 2 centuries. There originally were two main hypotheses as to Earth formation. First was catastrophism. Sorry if I mispronounced that. Essentially, this is more of a biblical-based approach, which in the Earth was formed quickly and catastrophically. Think Noah's flood. Eventually, we made way to a more modern look at geology, which would be uniformitarianism, or what you see happening today is what built the Earth. You see a mountain being formed, a river flowing, a sand dune wiping around, something being subducted. This is how it's always been, and these processes that we see today illustrate how the Earth formed in the way it did. The present is the key to the past. What you look at in the present tells you what happened in the past. James Hutton, widely regarded as the father of geology, one of the first real geologists looked at it from a pure scientific perspective instead of, again, going to Noah's flood or something like that as an explanation. Here's some examples of geology. Here we have some layered sandstone. Why does it have these layers? Why is it the height it is? Why is it sandstone? These are questions you can come to understand via this course and further study on your own if you want to. And it's, to be honest, super interesting. Here's a river, obviously. What is this river doing? How is this river affecting the rock and the sediment and the soil around it? 10,000 years in the future, what is this particular spot of land going to look like? 10 million years in the future, what is this particular spot of land going to look like? These are questions geology can answer. Here we have another example where I can ask the same questions with the river that I could ask here. And furthermore, how do you think this relates to the sandstone picture we just looked at? All three connected? Maybe. All right, so geologists. They are able to assign fairly accurate dates to events in Earth's history, i.e. how old something is. If you look at a rock or a piece of geology, you can date it via arguably two different methods. You can do a relative and absolute dating. Relative dating is when events are placed in a proper sequence or order without knowing the ages and years. For example, the dirt that is lower is older, the dirt that is higher is younger, right? That'd be a relative age. The topsoil in your garden is probably not been there as long as the soil 5 feet down, right? Absolute dating would be an exact date, an exact number of years that something is formed. The two processes intermingle and work together quite well. You don't always need one to have the other, but the more information, the better, right? Something that is hard to grasp about geology and is really only found in geology and astronomy and maybe biology in certain areas is the amount of time here. You think of someone who's 70, 80, you think, wow, they've lived a long time, right? On a geologic scale, we talk millions to billions of years of age. Those are numbers that are very hard to understand, right? What is $1 million? It's ridiculous understandings. And part of the way that geology works is using these millions and billions of years to get things accomplished. Sure, that beach that I showed a picture of earlier, you don't see that actively building geology on a day-to-day trip, right? Over millions of years, a different story arises. A classic example, if you've seen Cosmos with either version of Cosmos, you should know the analogy of the lifespan of the Earth as a calendar, wherein January 1st is the origin of the Earth, and as we go through the days of the year, we're following them on a geologic time frame. Notice here, we don't have life until March 3rd. So we get almost 3 months along in the geologic calendar before we have any real life at all, right? And even then, we have to go all the way to mid-November to begin the Phenozoic Eon, which is where animals and hard parts become abundant. So life, in a way that we would recognize it, doesn't start till mid-November. So again, if we imagine the Earth forming January 1st, think about how much of the calendar is soaked up with essentially no life that we would recognize on it, right? And you could punch us down and we go over here, this December clock, where we see the dinosaurs dominating the last couple of weeks of December. And we have to go all the way through this clock down here at the bottom to find humans, not humans like you and me, but humans as in Homo sapiens appearing 10 minutes to midnight. That's nuts, right? That's absolutely crazy. The Earth forms January 1st, and 10 minutes to the new year, December 31st, Homo sapiens appear. So hopefully you can understand when I say geologic time scale, I mean something that is more or less unimaginable in any other part of your life outside of, again, astronomy, geology, and arguably some biology. But even biology doesn't really start till mid-November. This right here is a geologic time scale. You can sometimes see this as a what's the word? I can't remember off the top of my head. Sedimentary rock sequence or something like that. Anyways, this is a way that geologists describe ages of the Earth. We use eons or eras, and then we chop them up into periods and sometimes epochs. An eon would be the largest chunk of time that we talk about. Over on the left here, we see Phenozoic or Precambrian eons. You can chop those up. The Phenozoic there, as you see, is exploded out into eras, the Paleozoic, Mesozoic, Cenozoic, and then those further are chopped up into periods. Notice here in the very center, the Jurassic. You know Jurassic Park, right? The time at which the dinosaurs that lived in the Jurassic period lived, and that's kind of a misnomer because Jurassic Park wasn't only dinosaurs from the Jurassic, is that particular period of time. You have to go all the way up to the top there, the Holocene. That's where we're in now, which is in the Quaternary period in the Cenozoic era in the Phenozoic Eon. So, you're doing geology. What are some base assumptions you have to make? One, the natural world is consistent and predictable. If something is happening now, you can assume that's the way it's happened in the past. That's the way it's going to happen in the future, right? Your battery is charged. You have gas in your tank. All the parts in your car are in functioning order. You assume when you turn the key, the car starts. If everything is in working order to make the car start and the car doesn't, that's something that shouldn't happen, right? That's not going to happen. If it did happen, then we're leaving the consistent, predictable nature of the natural world, which is something we don't actually see. If your car doesn't start, there's usually a reason for it. You're out of gas, your battery's dead, your alternator's busted, something like that, right? Your, well, I guess not the alternator, but the starter, for example, is fried. If everything is working and something doesn't happen the way that it consistently, predictably did in the past, that would be of note. But we have never seen that before, which is why science assumes, again, that the natural world is consistent and predictable. The goal of science is to discover patterns in nature and use that knowledge to make predictions. Again, if everything in your car is working, I predict when I turn over the key, my car should stop. The car starts, cool. Science, success. Scientists collect facts through observation and measurements, otherwise known as scientific method. You've heard the scientific method all throughout high school. That should be, I'm not going to go too deep into it. So, how and why things happen, I'll explain using usually a hypothesis. When you have a hypothesis, you can argue it's a tentative explanation. I think this is going to happen. Cool. If you think it's going to happen and it shows to happen and you change things and they continue to work the way you think they work, eventually you come across a theory. A theory we're going to define in this text as a well-tested, widely accepted view that scientific community agrees best explains certain observable facts. I'm going to stress this throughout this first chapter. The way some people use theory is not the way I'm using theory. When I say theory in a scientific context, it is in no way, shape, or form some sort of guess or unknown. A theory is something that is happening. Scientific method, as we talked about already, involves gathering facts, observation, to form hypotheses and theories. There's no fixed path that scientists follow that leads to scientific knowledge. Every scientist out there is going about maybe in slightly different orders. There's some interesting videos you can watch on that subject. But basically, the end goal is to form some sort of hypothesis to add to the knowledge base of science, expand theories, create new ones, things of that nature. That's the goal here, right? Geology, you could argue, is a largely observational science, meaning stuff you pick up in your hands. Geology does have a lot of calculations and modeling, of course, but compared to some other sciences, you get your hands dirty in geology. Part of the reason why it's so fun, right? So let's take a quick little 5-second dive into the scientific method. Look at this picture here. Cool picture, right? This picture here has some interesting stuff going on in it, right? Hey, Carly, I started at 6. It's fine that you're a little late. Couple slides in, you can catch up in the YouTube if you want. Chat's open. Feel free to type in the chat if you want me to answer any questions. And yeah, jump in whenever you want if you have a question. So, as I was saying, observation, scientific method. Look at this rock here. Look at this outcrop. What do you notice about it? What is interesting about it? Why do you think this particular outcrop looks the way it looks? I should ask before I go any further, Carly, can you hear me? You can type in the chat or respond via your mic, either way. Thank you. So you look at this outcrop here, and you can make what are known observations about it. Again, this is something that should be old hat from your science classes in high school and middle school, what have you. Observations you can make, well, you can make observations about the heights of the particular layers of rock, right? The angles, orientations of those layers of rock, the color perhaps, the grain size, which we'll get into what grain size is later. Do you notice any fossils in the rock? You can get a lot of information by looking at these particular outcrops. And then you could use that information following the scientific method to form a hypothesis about what went down, right? So if you watch this on YouTube, take a few seconds, pause the video at this point, predict what do you think occurred in the past to produce the rock in the present that looks like this. I'll assume you pause the video, I'll just move on. Oh, and again, I'm going to, Carly, just so you know, I'm going to be interacting with the video as if it's a YouTube video. Of course, jump in with any questions, but if I say I'm going to pause and let you think about it, I'm going to move on right away, right? Just want you to be aware of that. So we can look at where cross beds form today, and perhaps that gives us a clue as to how that rock formed the way it formed, right? The present is the key to the past. The idea of uniformitarianism, the idea that geology, that the way geology is working today is the way it has been working, because we've never seen it not do that. So if we look at rivers, beaches, and dunes, we notice they can form sand in a very similar way that is formed here. Likewise, we notice that this sand is about the same grain size as this sand, and perhaps this sand is a similar color to this sand. All those things line up. Maybe there's a connection between the dunes and the beaches and the rivers that are forming on Earth right now and the geology that we see like this that was formed on a geologic scale in the past a while ago. Couple things again to beat this idea into your head. Results don't prove hypotheses or predictions. They confirm or refute them. They don't prove anything. Technically, in science, you should never say prove, because there's no 100% certainty in science. You can, if I drop a fork and it falls to the ground, that confirms the idea that gravity is doing that. It doesn't necessarily prove gravity, because there is that chance that I drop a fork and it flies up into the sky. Oh, well, now gravity has an issue, right? That's not going to happen, obviously, but this is why we don't use the word prove. Hypothesis becomes a theory, and that's becomes a theory is not necessarily like it graduates, or more so the scientific body assumes it as a theory, when there's a massive body of evidence that supports it. A theory in science is not a guess. Again, I said that earlier. I'm going to repeat it here. I'm going to beat that into your head. A theory in science is not a guess. The theory of gravity is not the same thing as I think this is going to happen. The two are very different on all shapes and sizes and forms. Sweet. So let's talk Earth spheres. Earth, small rocky planet. Cool. We know this to be accurate, exciting, how fun. The Earth, we can describe the Earth as having 4 spheres: a hydrosphere, an atmosphere, a biosphere, and a geosphere. I'm sure you can look at those and figure out what they are involved with, but I'll get into it anyways. First, the hydrosphere. This is all the water on or in the Earth, and I need to go into this slide and fix that spelling. Fantastic. The majority of the water on or in the Earth is in the oceans. In case you didn't know, oceans are kind of big, right? Of that, about 97.44% of the Earth's water is salt, saline water. 96.5% of that is in our oceans. The fresh water, the water that we drink, only makes up about 2.5% of all the water on Earth. And of that 2.5%, a vast majority of it is in glaciers, frozen, at the North and South Poles and Greenland, stuff like that. Of that, we get to the point to where we have a tiny, tiny portion of Earth's water is liquid fresh water. And the majority of that liquid fresh water is groundwater. This is the stuff that, we pump out of the ground. Your faucet, probably 9 times out of 10, 99 times out of 100, your water that you turn on from your faucets pumped out of the ground is groundwater. The fresh water, rivers, lakes, and streams that we see, that we deal with on a daily basis, make up 0.003% of water on this planet. 3/100ths of 1%. Tiny amount of water. And again, if you're a GCC student, you're used to the Great Lakes. They seem gigantic, right? They are nothing in comparison to the oceans or even the glaciers. Heck, even the groundwater. It's pretty mind-boggling when you think about the scope of the hydrosphere. Next is the atmosphere. The atmosphere is, well, the gaseous presence here on Earth. The air we breathe, the air we don't breathe, the clouds, things of that nature, air pressure, all that. I don't go very much into the atmosphere in this class because it's a geology class, right? But the atmosphere is another sphere of the Earth, and it is all the gases that we have. The biosphere, this is the stuff that lives. If it lives, it's in the biosphere. Doesn't matter where it lives, it's on the biosphere. Here we have fish, plants, sea creatures, humans. I'm part of the biosphere. You're part of the biosphere. Congratulations. That's the biosphere. And lastly, certainly not least, the geosphere, the solid Earth, the largest of the Earth's spheres. Everything from the surface down to the core is the geosphere, including the soil. That's the point of this class, right? To learn more about the geosphere and just how fantastic it is. And you will agree with me. I grade your papers. So, within the geosphere, we have 3 different types of rocks. The geosphere is comprised entirely of these 3 rock types: igneous, sedimentary, and metamorphic. Igneous rocks, as described here, are fire-formed. These are the result of volcanic eruptions and extrusions, or I guess intrusive as well as igneous. We'll get into each of these in their own chapters. You learn more about these 3 types. Sedimentary rocks, you could argue, are rocks formed at the surface. These, there's a whole rock cycle we'll get into. And finally, metamorphic rocks are rocks that are changed or altered in some way. All very unique, all play a huge role in forming the Earth the way it exists, and all have their own fun little parts to them. Good times are had. Very famous picture, Earthrise. This is very low res. I'm going to have to replace this with a higher res version. That looks horrible. But yeah, that's the entirety of the Earth. The geosphere, biosphere, hydrosphere, and atmosphere all encompassed in this picture right here. Pretty cool stuff, right? And again, I guess this picture also goes into, we do geology on other planets. There are some of the astronauts that went to the moon were geologists there specifically for that purpose. So you can do geology on other planets, or moons in this case. Yeah, pretty cool. So Earth as a system. Let's talk about that. The Earth is a dynamic planet with many interacting parts, right? Parts of the Earth systems are linked. In this class, after we go through the basic rock types, we're going to go a lot into Earth systems and geologic systems and how they interact and how they make the world exist the way it exists in a way that you live on it. You can characterize these processes by spatial scales or time scales, fractions of a millimeter to thousands of kilometers. And a lot of the processes we're going to talk about, a lot of the dynamic interactions that take place in the geosphere on this planet span that spatial scale. The same thing that causes a fraction of a millimeter change will cause that exact same change on a continent-wide basis. Variable timescales kind of works in the same way. Some geo-related events can happen almost instantaneously. Some geo-related events take literally billions and billions of years to happen. More so the millions and the billions usually, but we will get into that, right? It's only chapter 1. Picture here, intersection of 3 spheres. What 3 spheres? I think it's pretty obvious, right? You have the atmosphere, that's the clouds, the haze, the hydrosphere, the crashing water, and of course the geosphere causing that water to crash. Truth be told, I'd be surprised if there wasn't a fish someplace in this picture, or a bird. That would be very shocking to me. I'm sure there's bacteria someplace in this picture. So there's probably actually all 4 spheres interacting. And all 4 need to work together to produce the planet that we live on. The hydrosphere beats up the geosphere affects the atmosphere, and the atmosphere allows the biosphere to exist. They all interwoven in this wonderful planet we call Earth. And probably every other planet, I imagine. Earth is a system. The Earth is powered by the sun, which drives external processes in the hydrosphere, atmosphere, and on Earth's surface. I'm sure you're aware of the sun. You've probably seen it before. Don't look at it. It's why summer is warm. It's why winter is cold. It's why ice forms. It's why ice melts. If I have to explain the sun to you, you need to get a hold of me because you have a lot to catch up on. The Earth systems are also in part powered by the Earth's interior. This one's a bit cooler, in my opinion. When the Earth formed, it formed via heat, right? We'll get into how igneous rock is formed, but there was a lot of heat involved in the formation of the Earth. And that heat still exists and is still actively being generated in the Earth's interior, in the Earth's core. It is actually generated by radioactive decay, which is a very interesting process and kind of ridiculous to think about. Underneath your feet right now is a massive radioactive ball of molten metal. And that's pretty sweet. This is a good XKCD comic about that, if you read them at all. Both power the internal processes that produce volcanoes, earthquakes, mountains. When we get into igneous and metamorphic rocks, I'll explain this stuff more in detail. So, how did the Earth form? Well, classically, we think the universe began with some sort of big bang, some sort of expansion of space-time. This class doesn't really dive too deep into that, but it is itself, it's a super interesting thing to look into. The Earth and all the other planets formed around the same time and out of the same material as the sun. Accreting and things of that nature, again, cool processes, but more or less we think that the planets in this solar system all formed around the same time, or on a geologic scale around the same time. You know, there may be millions and millions of years between them, but millions of years isn't a big thing in terms of billions, right? Nebula Theory proposes that the bodies of our solar system evolved from an enormous rotating cloud called a solar nebula. This is something that's actively going on nowadays. Other solar systems, other planets are being formed by the same process that we think formed us, which is why, as I said before, the present is the key to the past, which is why we believe our solar system was formed via nebula, because we can watch it happen in other parts of the universe. Cartoon of this process. The process is obviously a lot more complicated than what's going on here. That being said, this gives a good understanding of it. Birth of the star system begins as dust and gases, a nebula that collapse because of the gravity of the collapse in on itself due to gravity. This collapsing causes rotation, coalescing into rings, which then those rings coalesced and brought back down into planets. Again, this class isn't about this stuff, so I'm not going to go too deep into it. If nebula theory is something that you're interested in, please take the time, learn more about it. It's very, ask me if you want outside of this particular class setting if you want, or right now, I guess, if you want to ask me something too, that'd work. So as I continue to say, nebula theory states that the nebula consists of hydrogen and helium, the two most common elements in our universe, because they're the most simple, right? Disturbances cause them to coalesce, cause them to clamp together and form, creating inner planets of metallic and rocky substances and outer planets of ice and gases. This is due to the closeness to the sun. If you notice, the rocky planets are more or less closer, and the icy and the gaseous planets are further away, right? Over time, again, due to gravity and other things, the heavier elements fell down in the bottom, creating a solid inner core. Solid, we think to be iron inner core. And outside of that, we had a somewhat liquidy outer core of nickel and iron. Then outside of that, we had a plasticky mantle, followed by a solid crust. This is the internal structure of the Earth. We know this pretty well via seismology, more or less. Again, that's the cool thing about taking a class like this is literally like every chapter, every couple slides is itself its own deep and interesting rabbit hole. So if something like this is of interest to you, there is a massive swath of information. Shoot me an email, ask me. I can provide you links. You can just start on this journey if you want. But something to take note here is the relative sizes of the different layers of the Earth. The common analogy is the Earth's structure is similar to an apple, where the thickness of the skin of an apple is about the same as the thickness of the crust or the lithosphere of the Earth. To give you an idea, I mean, you think of the Earth's crust and the size of mountains and the depths of oceans and all that pales in comparison to just how big the Earth actually is. Why did the Earth form the way it's formed? Well, we know denser objects sink, right? So the metals, the iron and the nickel down there, sunk down to the bottom to form the core. And then the stuff that was less dense, like the rock, rose up to the top to create the crust. Chemical segregation established the three basic divisions of the Earth's interior, along with gravity, as I said before, and a primitive atmosphere evolved from volcanic gases. The Earth originally did not have oxygen on it. Oxygen showed up later in what we call the Great Oxidation Event. Weird concept, right? But the science seems to verify this fact. Internal layers defined by chemical composition and physical properties. And these layers also defined by compositions such as crust, mantle, and core. Things I've already talked about. These slides go into more detail about it. Of course, I said if you have the text, dive into the text. You'll find it also to be providing you more information. But hopefully you're understanding the concept I'm trying to present here, which is the segregation of the Earth's structure. There are four main layers, as I said before: a solid inner core, a liquid outer core, a semi-plastic asthenosphere or mantle, and then a solid lithosphere or crust. Shown here again. Fascinating. We now have a concept, a very basic concept of the formation of the Earth and why the Earth looks the way it looks. Now we can talk about the rock cycle. The rock cycle is essentially the life of a rock. No rock is permanent. The rocks that you see in front of you at some time in the past were different. If we go back a couple slides here, I point out the earliest primitive crust is lost due to erosion geologic processes. Because, as you notice, as we get lower, the crust itself is solid, but below that is a semi-plasticky, malleable mantle. So the rock cycle shows and illustrates the processes that the rocks that we walk on every single day have underwent in the past and will undergo in the future, as shown here. The cycle, we're going to dive deep into this. You're going to hopefully understand this process soon, but you notice that it's not just a simple circle of igneous to sedimentary to metamorphic back to igneous, but there's also arrows going back and forth, connecting each particular rock type to each other rock type. And actually, sedimentary should also go back to igneous. I missed that. But basically, every step along this process connects back to each other one. And it's pretty cool stuff. Again, introducing this concept now, we're going to dive deeper into the rock cycle as we go through the class, because it's kind of hard for you to understand the rock cycle without understanding the rocks, right? Face the Earth. Let's talk Earth's surface, talk continents and oceans. What are the continents? The continents are consisting of mountain belts, which I'm sure you can picture are mountains, right? Most prominent features, and stable interiors such as shields and stable platforms. This map down here is a good example showing these differences: mountain belts and shields. You can say these sort of a highland and a lowland, if you will. Mountain belts, very tall, right? Shields, low hanging. The Brazilian shield, for example, holds, and the Orinoco shield, I don't know if I pronounced that correctly, holds the Amazon basin, right? That is downward sloping. The rivers go from the Andes Mountains down out into the Atlantic. new and old mountain belts exist. When we go into mountain building or genetic events and igneous and metamorphic formations, you understand why mountains have different ages like that. And hopefully you can understand a bit about the shields and the stable platforms. But the interesting point to take away now is that the map and the way it looks in our current form was not that 10 million years ago, or 50 million years ago, or 100 million years ago. All of this would have been different. Ocean basins, that's right where the ocean is. No surprise there. They comprise mainly of continental margins, which is where the ocean and the continents meet, deep ocean basins, which is the ocean floor, essentially, your abyssal plains, seamounts, what have you, and then oceanic ridge systems. Again, we'll go into this in more detail in later chapters, but your oceanic ridge system is where your ocean crust, your ocean soil, your ocean is actually formed. Mid-Atlantic rift system would be the most prominent example of this, or the Ring of Fire, if you want. Picture shown here of the oceans. I'm sure you've seen a picture of oceans before. I don't need to go too deep into this, but over the course of the following chapters, what you hopefully will understand what all those little lines and dots and islands and why they exist, where they exist, and how they exist, and the ocean's relationships to the mountains, to the shields, to everything. As I said previously, everything in geology is interwoven and works together to create what we see as we see it. Cool. So that is chapter 1. I hope you enjoyed it. In class, I go over a couple questions just to remind you of what we talked about. I'm not going to really do that for the online portion because you can just go back and watch it if you want, right? Yeah, that's all I got. Any questions from the attendants today? If you got a question, you can mic up or you can raise your hand, say it in chat, however you want to do it. No? All right, well, that's good then. I will end this meeting then. Thank you for attending. Make sure to leave comments and questions in the comment section below. Contact me via email for anything you need. And I'll see you for chapter 2 later in the week.